Hi, welcome to this session about OAuth and OpenID Connect in single-page applications. In this session, I'm going to cover recent changes, how single-page applications handle OAuth and OpenID Connect. As a running example throughout the presentation, I'm going to talk about a restaurant review application known Restaurate. I'm a chef myself, and I like food, so this was a logical choice for one of my training applications. Restaurate is very much like any other review application. You have a list of restaurants, you can post a review, and so on. Restaurate itself has a bunch of APIs, a front-end application, a mobile application, and so on. And what's important here is that the APIs are exposed to partner websites, allowing them to build applications around Restaurate's APIs. That's essentially the use case for OAuth and sometimes OpenID Connect as well. Before we dive into details, I want to give you a small introduction to OAuth and OpenID Connect, just so we're on the same page. On this image here, you can see the different stakeholders in an OAuth or OpenID Connect flow. You have a bunch of clients, different client types, such as a backend application, a mobile app, a front-end web app, or even a client with no user involved, such as a batch script. You have a bunch of APIs that need to be protected against access from these clients. And in the middle, the glue between all of this is a security token service, also known as an authorization server in OAuth terminology. What's going to happen is a client is going to contact the security token service to ask to authenticate the user. That's OpenID Connect. It's going to ask to access APIs on behalf of the user, and it's going to get an access token to do that. With that access token, the client can now go to an API and ask to perform certain operations, such as fetch information or make a new review in the database. The APIs, in turn, rely on a security token service, either directly or indirectly, to actually figure out if this is an allowed operation, yes or no. They need some information to make that decision. This picture is a very, very high-level overview of OAuth and OpenID Connect. OpenID Connect is about authentication. It's a client asking the security token service to handle user authentication and provide it with authentication information in an identity token. OAuth is about accessing protected resources, APIs. OAuth is about asking for an access token. Those are the main OAuth flows, and it's about using the access token. OAuth also specifies how the API should decide, or what information the API can use to decide if certain operations are allowed. And that's what this picture really puts into place. Keep in mind that OAuth is a very elaborate landscape. It's a bunch of specifications that all tie together into this one specific authorization framework. Some of the arrows on this image are underspecified and some are very well defined, but we'll talk about that a bit later. If you're familiar with OAuth and OpenID Connect, you may have noticed that I'm using different terminology than you might read in the specifications. One of the reasons here is that the terminology in the specs is often very broad because it allows various scenarios which are not relevant for single-page applications contacting APIs. The second thing is that OAuth uses something different than OpenID Connect, and swapping between both is going to be a nightmare to follow along. That's why I'm using users, APIs, clients, and a security token service in this session. On the right, you can see what that translates to in the OAuth specs or in the OpenID Connect specs, in case you want to go there and read them. All right, before we dive in, a few small words about myself. I'm Philippe de Ryck, and I'm from Belgium. And I used to travel the world to help people with security. So I did a PhD in security, and since a few years, I'm running my own consulting and training company called Pragmatic Web Security. And I travel the world, or I teach online nowadays. I teach developers how to build secure applications. I create online courses, and I also deliver security advisory services to developers or companies building out very specific solutions. So one of the solutions is how can we build single-page applications according to current best practices when we use OAuth. At the top here, you'll see a few icons. Noteworthy here is I'm a Google developer expert and an Auth0 ambassador, which basically means that these outreach programs recognize my contributions for security and identity to the community, very much like this talk I'm doing right now. Enough about me. Let's talk about single-page applications. Let's go back a year, maybe a year and a half, and see about how a single-page application would request an access token from the security token service. And that application is going to use the implicit flow. What does that look like? Well, we have our front end at the bottom here. We have a browser from the user. We have our security token service on top. And eventually, we're going to be contacting an API with an access token. The first step is that the front end is going to navigate the user's browser to the security token service, because this step allows the STS to figure out who the user is so it can give appropriate access tokens for that specific user. This happens with a navigation, so the browser is going to follow that navigation, load an HTML page, or send a request to the security token service, which will trigger the whole flow. That's step number 2. The STS at this point is going to decide, do I know who the user is? Do I have an existing session? If so, I can move forward, but typically it's going to have to authenticate the user. So it's going to show the user an authentication page like, who are you? Can you log in with your retrograde credentials, please? Oh yeah, of course, I'm Philippe, and this is my password. Here you go. STS verifies that information, and if everything checks out, it now knows that Philippe authenticated to the security token service. In this case, it might check with the user if the user is fine with sharing access with the retrograde front-end application. So basically, the STS is asking the user, I'm going to give that app an access token. Are you sure you want that application to act on your behalf to the API? In this case, the user obviously wants that, so the user authorizes that access. That's step number 6. You may have noticed that OAuth flows get complicated really quickly, but we're almost there, I promise. So after authorization, the security token service is going to generate an access token, essentially what we want to achieve with our OAuth flow. And it's going to trigger a redirect in the browser. So it's going to respond to the user's browser with a redirect, telling that browser to reload the front-end application. And it's going to include that access token in the URL of that redirect. The browser is going to reload the front-end, which allows the front-end to extract the access token from the URL, which it now gives the front-end that desired access token. And with that access token, the front-end can now go to the API and ask for a specific set of reviews, and will get a response from that API as well. And that is how front-end applications actually request access tokens or requested access tokens. People sometimes kind of dislike the implicit flow. It's one of the simpler flows in OAuth. That's one of the benefits, but it also has this glaring problem here. This is something that rubs people the wrong way. And that problem is the fact that this access token is being transferred in the front channel through the browser. That means if somebody is observing the network traffic, they can steal that access token right there from the URL. Fortunately, this is no longer that big of a problem. It isn't as big as 10 years ago when this spec was created, because today everything runs on HTTPS. Nonetheless, people don't really like it. It's not a good practice to put things in URLs, so this is a bit frowned upon. Also, this particular pattern here is the reason that the implicit flow does not support refresh tokens, which would allow long-term access in the name of the user to that API. But we'll talk about that in a bit. So the implicit flow isn't great. And it used to be acceptable because that's the best we could do. But recently that changed, because recently the best practice became to use the authorization code flow with proof key for code exchange, or PKCE in short. This flow results in the same thing. It also results in an access token. It just takes a little bit longer to get there because there's an intermediate security mechanism called an authorization code. And that code is going to be a one-time token that goes through the browser that doesn't do anything else but give access to an access token. So let me show you how such a flow works in practice. With PKCE, the client is first going to generate a random verifier. That random verifier is a long random string that matches certain rules in the specification. The exact rules aren't too important right here. Next, the client is generating a hash of that verifier, like basically a unique value linked to this verifier that can never be linked back unless you know both values together. And that challenge is what the client will use to start the flow. So again, the client is going to navigate the browser to the security token service, but now it says, hey, I want to receive an authorization code in return. And by the way, here's my PKCE code challenge. Keep track of that, please. The STS behaves very similar to last time. The STS is going to ask the user, who are you? Oh yeah, I'm Philippe with beer and fries 17 as password. Awesome. I'm Belgian, so why not? But I digress, so not too important. If authorization is required, it's going to check for authorization. And if everything checks out, the STS is going to be happy. The STS is now going to keep track of that code challenge along with the authorization code. Remember, the authorization code is a unique code valid for one-time use, and that's what the STS sends back to the browser. Browser loads the single page application again and gives that application the authorization code through the URL. All right. So now we're back at the front end. So the user sees, or the front end is being loaded again, and that front end can now extract that authorization code and go back to the security token service to ask like, hey, I got this piece of random junk. What does this mean, please? So the client goes there and says, I got this authorization code. And by the way, this authorization code is linked to this challenge, and this challenge is linked to this specific random verifier. So I'm the legitimate client exchanging this code. Awesome. The STS is like, we'll see about that. That's what you tell me, but I'm going to verify that. So the STS will actually recalculate the hash of that verifier, compare it to the code challenge stored along with the authorization code. And if all of these things check out, the STS will be happy, like, oh yeah, you are the right client. This is not an attack. This is not an injection. No, you are the actual client. And that's cool. And this authorization code, I remember that I gave that out in the URL, and that's associated with Philippe's account because Philippe authenticated during this flow. So you know what? Since everything checks out, I'm giving you an access token and a refresh token and an identity token. And that access token is what we're after here. That access token is what allows the client to contact the API on behalf of the authenticated user in step 5, and that's Philippe. And that's what OAuth, or this flow, is all about. With the identity token, the front end obtains a bit of information about the user. It contains the user's name and a bit of information, allowing the front end to customize its UI a bit. And then, of course, with the access token, we can go to the API and make that request. This is by far the most complicated flow you'll find in the OAuth specifications. This is the current best practice for running an OAuth flow with single-page applications. OAuth or OpenID Connect, it's the same flow, just different parameters in certain steps. So what does this look like in practice? What if you dig down, deeper down into the actual requests and responses? That's where you see all of these parameters flying back and forth. Let me show you the request for step 2 and 3, the redirect URI. So that's basically the step where the front end, the SPA, navigates the browser of the user to the single page application. You can see this is going to be a very long URL. In reality, they don't look very pretty. They're just a long blob of data. So I PowerPointified this one for you so you actually understand what's going on here. On line number 2, you can see a response type. That's the front end telling the STS, I expect a code, an authorization code in return to my initial request. Awesome. By the way, I am the REST-grade frontend. This is a client identifier that has been assigned by the security token service at the beginning when the client was registered there. There's a redirect URI, which basically tells the STS, when you're done and you want to send me a code, I expect you to call this particular URL to load the application and allow me to extract it from the URL as well. And then at the end, we have that code challenge. That is a Pixie-specific code challenge. That is the hash of that random value. And this is the hash, and the last parameter, line 8, is the hash function being used, which is SHA-256 in this case. And that URL will bootstrap or kickstart the entire OAuth flow. It contains everything we need to get started. All right. Next up is step 11. In step 11, that's when the client is going to go to the STS to exchange that authorization code for tokens. So essentially, we call that the token exchange, which is, or the code exchange, sorry. It's a code exchange, which is fairly straightforward naming-wise. This is a post request, but again, you can see it's very similar to the previous one. It contains a bunch of parameters to make all of this happen. First line indicates that we're exchanging an authorization code for tokens. We indicate who we are. This is the client from before. It's the same identifier. We specify where we received this code. That's necessary for certain reasons, which I'll not go into detail. And of course, we also provide the random code we received from the authorization, from the security token service in step number 9 and 10. And then finally, that's Pixie specific again. We provide that random string that we generated in step 1 that proves that we are a legitimate client. So if an attacker is messing with an application and trying to inject tokens, it will codes to trick the client into doing something it's not supposed to be doing. It will not match this code verifier, and the STS will be refusing that request. This is again a recent addition that adds additional security to the integrity of the flow. Very important. All right, I am pretty confident that by now you are in a full-on panic mode if you ever have to implement this. Like, holy, I'm not going to swear here, holy whatever. What the hell is all of this? How do I implement that? Well, honestly, you don't. I don't recommend you implementing all of these dirty details, because I can guarantee you it will take you a long time to figure all of that out, especially the specific encodings and character sets you have to use and so on. Instead, I recommend that you use a library. If you're building an Angular application, there's at least 2 or 3 libraries that you can use that have this out of the box implemented. Same thing for React applications and the other frameworks as well. Auth0, one of the identity providers or security token services running in the cloud, has a generic JavaScript SDK you can use for any framework. They also have specific SDKs, but this one that I'm showing you right here is generic for all frameworks. And you can see that we configure that SDK with the necessary parameters. We tell it where the STS lives. In this case, it's sts.restograde.com. We provide it with our client ID. We set the redirect URI, which is this application, and so on. That's the configuration step. Running the whole flow that I talked about, the whole authorization code flow with Pixie and the random value and a hash and all of that, is 1 line of code. Login with redirect. That's it. By specifying that line of code, the SDK will know what to do. It's like, aha, I know how this works. I am configured to run an authorization code flow with Pixie. So I'm going to go for that. I'm going to run this initialization. I'm going to get that code in the callback. I'm going to make the API call to exchange that. And I will get some tokens to run or to access an API with. And that's why I recommend to use a library, because the library is implemented correctly. And this Auth0 library supports Auth0 specific features if you want to use them. And that brings us to the first takeaway in this presentation. The implicit flow is deprecated in favor of the authorization code flow with Pixie. That's a very important realization. This doesn't mean that the implicit flow is broken or more broken than it was a year ago. That is not the case. There's no new vulnerabilities. What simply happened is that we have a better alternative, and I'm going to talk about some additional benefits in a second, but we have a better alternative, so the recommendation is to use that today instead of the implicit flow. And the reason we have something better is because our SPAs, our browsers, got better and are capable of doing cross-origin API calls to do the code exchange and so on. So technology got better, and so did the OAuth flows. What does this mean in practice? This means in practice that if you're building a new application, you use the authorization code flow with Pixie for any front-end web application as an OAuth client. If you're building or if you're working on an existing application that already has an implementation of the implicit flow, you don't need to panic. You're still okay to use that. It's still fine to use the implicit flow, but you should put upgrading to the authorization code flow with Pixie on the roadmap so you can do that in one of the coming months. That's basically the current state of practice or the recommended best practices today. All right. In the second part, I'm going to be asking a bit of questions. Of course, I'll answer the questions as well, but it's going to be a question and answer part of the presentation where we're going to dig deeper into certain cases and look at what we should be doing there. The first question is, what if an access token expires? Access tokens in the front end are somewhat vulnerable. They're in a browser. Browsers are not the most secure environment. What if one of them leaks out? That's why these access tokens, where the front end accesses API switch, should have a limited lifetime. 5 minutes, 10 minutes, that's actually kind of recommended to have them that short. That also means that the access token will expire at some point. That means that the access token will expire in 5 minutes, and that the front end will no longer be able to access that API. So how can we fix that? Well, that's where the refresh token flow comes into play. A refresh token flow allows us to obtain a new access token. So the starting point for this flow is a front-end application that already has an access token and a refresh token. It can monitor when the access token expires, or it gets an error from the API saying this thing is expired. And that's when the front end kicks into action. The front end is going to send a request to the security token service with that refresh token to ask for a new access token. Of course, the security token service is going to verify that request. There's going to be a bunch of parameters to check. And if everything checks out, and if the refresh token is valid, it will issue new tokens. So the security token service responds with an access token. And with that access token, the frontend can now go to the API and make the request it wants to make. All right. You may remember from about a year and a half ago, that people have been saying, never use refresh tokens in the browser. And they were correct, absolutely. So what the hell is this about? So refresh tokens in the browser were not allowed with the implicit flow, but they are allowed with the authorization code flow. So this refresh token flow is now available in the browser. But there's a very, very big caveat here. There's something we need to think about, and that's what happens if an attacker steals tokens from a single page application. What happens if the attacker is able to extract a refresh token that gives long-term access? Then they can abuse that for 12 hours, 24 hours, 36 hours. I don't know how long it's valid. And they can abuse that to get new access tokens and keep posting reviews in the name of the user. This can turn out really well or really badly. Depends on the intentions of the attacker and the restaurants they're targeting, of course. So that's a problem. And that's a big problem in single-page applications because there's so many attack vectors for that happening. One example is user-provided data. User-provided data can lead to something known as cross-site scripting, which would mean that the attacker is now running JavaScript code inside the application. Remote code inclusions can get compromised. We've seen plenty of cases like that, where a file from a CDN contains malicious code and is now running in the application context. Advertisements can become malicious as well, can cause similar problems. And if you deploy a new version of the application with a vulnerable NPM dependency, that can also lead to malicious code running in the application. And let me tell you, once malicious code runs in the application, it can probably access your token. So that's a bit of a problem. And that's why you're not allowed to use plain OAuth refresh tokens in a single page application. You can only use refresh tokens when they follow an additional security mechanism known as refresh token rotation. And that mechanism was first defined in an addition to the OAuth 2 spec for browser-based applications and is now part of OAuth 2.1, which is in a current draft. In essence, refresh token rotation is a fairly simple concept. I'm going to explain that to you with a timeline. The application or front end obtains tokens. Access token 1, which is AT1, and refresh token 1, which is RT1. And access token 1 has a limited lifetime of, let's say, 10 minutes. What the application will do is, before that access token expires, it will request new tokens. It's going to use the refresh token flow along with RT1, goes to the STS and says, hey, I got this RT1 here. Can you give me new tokens with RT1? The STS is going to verify all of that. And in this case, it will issue access token 2 and refresh token 2, AT2 and RT2. At that moment, RT1 becomes invalid. Next time the application notices that the access token is about to expire, so when AT2 expires, it's going to run the flow again with RT2, and the STS will issue access token 3 and refresh token 3. And again, when access token 3 expires, the whole flow is going to happen again. And this keeps on going until the application is terminated, until the user closes the application. That's essentially how a front end can work with short-lived access tokens and use refresh tokens to obtain new ones. This mechanism, like I said, it's fairly straightforward, but it's only part of the picture. Because what if an attacker steals RT2? Then still bad things can happen, right? So the missing piece of the puzzle here is the security token service detecting refresh token abuse. And here's how that happens in practice. So on top, on the blue, we have our legitimate application running its refresh token and access token dance, like expires, get a new one, expires, get a new one. At some point in time, the attacker manages to execute malicious JavaScript code and steals refresh token 2. Takes it out, sends it to a server from the attacker, and can potentially abuse it. The application has no idea that this happened and just goes on like before. Token is about to expire, let's get a new one. However, since the attacker stole RT2 through cross-site scripting, for example, the attacker can now use refresh token 2 as well. However, the security token service will be looking out for that. When it receives the refresh token 2 from the attacker, on the right here, it will look at its list of refresh tokens and notice, hey, I already saw that token before. What the hell is going on here? And it's not even going to think like, should I allow this? No, it's going to be like, hell no, boom, done. And it will revoke refresh token 2 and every token associated with that refresh token. So it will kill all tokens on the slide right here. And that is to prevent abuse of a stolen refresh token. That's essentially how this protection mechanism works. And the same mechanism is applied in a variation of this scenario where the attacker is first. So in this scenario, the setup is the same. The attacker steals a refresh token, but uses it first and obtains a new access token and a new refresh token. The application, again, is unaware that this happened and will try to do the same itself 5 minutes later. And at this point, the security token service will detect this. The security token service will say like, hold on, I already saw RT2. That is not good here. And it will revoke every token on this slide, including the attacker's tokens. And that's why this security mechanism is so important. And that's why we're allowed to use refresh tokens in single page applications, because we have this security mechanism in place to prevent abuse in case they are stolen. So problem solved, right? If you see a slide like this, probably in any presentation, but especially in a security presentation, the answer is always like, probably not, no. So the follow-up question is like, what is the remaining problem then? And the remaining problem comes from this seeming misunderstanding of the power of cross-site scripting. So all of this that I talked about now is part of the specifications on how to protect refresh tokens. But the problem is your application is executing attacker-controlled JavaScript code, and the attacker can do whatever the hell they want. Whatever you as a developer can do, the attacker can now do as well. And there's a couple of scenarios where they can avoid detection of stolen refresh tokens. And in my opinion, refresh token rotation doesn't buy you much. Let me show you 2 scenarios. There's a couple more, but I only have time to cover 2. And I'll let you make you up your own mind after that. So how can an attacker sidestep refresh token rotation? Bear in mind that these are advanced attackers, like the skilled people coming after you, not the script kiddies that found a way to extract information from local storage and don't really know what a refresh token is. But a skilled attacker will do something like this. We have our application running on restofpage.com, and we have our attacker-controlled code right in there. Doesn't matter how it got here, we have a piece of malicious code running in your application. That code is going to monitor legitimate application code for tokens. And whenever your legitimate application uses an SDK to get new tokens from the STS, the attacker will be monitoring that process. So the attacker will now be able to extract access tokens and refresh tokens every time you get a new set. And the attacker sends these tokens to the server controlled by the attacker, just extracts them and ships them off so the attacker can use them later. And then the attacker waits. And maybe this happens again and again, and the attacker does the same thing again and again until the application becomes inactive, until the user stops using this application. And at that point, you'll have some refresh tokens still valid. RT5, maybe RT99, I don't know. One of these tokens will still be valid. So the moment the attacker detects that the application went offline, it can start using that refresh token itself to get new access tokens and new refresh tokens. And it can basically keep that refresh token alive or that chain alive until it reaches its final lifetime. So refresh tokens in the browser will have a finite lifetime, as in 8 hours, and after 8 hours, it's over, and there's no way to go on after that. But the attacker will now be in control of that refresh token. That's one scenario. A second scenario is just ignoring refresh tokens and only stealing access tokens and abusing them. How does this work? Very similar setup. We have our application with an SDK running a flow with a security token service, and the attacker code will be monitoring that flow again. So whatever tokens it can access, it will extract them and send them off to the attacker server. In this case, it's only an access token, no refresh token. There's some trick to hide the refresh token, but not the access token, because the application actually needs that token. And of course, the access tokens, once they're extracted, the application or the attacker can use them just like the application does. So now the attacker can post a review in the name of Philippe. And if the application remains active and the payload of the attacker remains active, the access tokens will keep coming, and the attacker will be able to keep posting reviews in my name until the application gets shut down. Then, of course, the attack here ends. And these are fairly sneaky attacks, and it seems that we should be able to protect tokens, but I can promise you in JavaScript, you really can't. And if you want to know more, there's an article I wrote about how to extract them from one of the most secure setups I've seen, where they hide the refresh token, but the access token, because it's passed around, will always be accessible through some dirty JavaScript tricks. So remember, in JavaScript, you cannot hide secrets, ever. So I promised you question and answer, so we're screwed, basically, right? Well, yes, in this case, the answer is yes. Tokens in the browser are virtually impossible to secure. And that is something that you'll have to live with. Honestly, I wish I would have better news, but I really don't. If you have tokens in a browser-based application and you have malicious JavaScript executing there, tokens will be extracted. There's no doubt about it. It might be difficult, and maybe not every attacker will be able to do it, but somebody will extract these tokens. So what do you do for sensitive applications? Well, my advice for sensitive applications is not to store tokens in the browser. Instead, you should use a concept we call a backend for frontend. And I'm going to introduce this concept to explain you conceptually what it does, and then we're going to wrap up this session. So what is a backend for frontend? Well, in a backend for frontend, we're going to build a specific dedicated backend for our frontend application. And that backend sits in the middle between the frontend, the security token service, and the API. It's part of retrograde. So this backend is a retrograde backend serving the retrograde frontend. It's not an API. It's actually simply a proxy service. The frontend and the backend run in the same domain. They maintain a traditional session, a cookie-based session. Yes, dirty, maybe, but it works. We can hide cookies, we can protect cookies, and we can maintain sessions even on the client if you prefer. You can make that backend stateless without issue. The key aspect of a backend for frontend is that the backend, or the BFF, basically becomes our OAuth client application. It's no longer the frontend that's going to request tokens and attach them to requests. No, it's going to be a backend. That backend is going to run an authorization code flow with client authentication for backend web applications, and it's going to get an access token and a refresh token. And whenever the frontend makes an API call, it makes that call to its backend. The backend will forward that to the actual API and attach an access token on the outgoing request. So as far as the API is concerned, things work as they did before. The API has no idea that this is actually a different client making that request. And that's what we call a BFF. And this is better because now tokens remain in the backend. And additionally, the backend can follow OAuth security best practices for backend web applications, which are much more secure than those for front-end applications. Two examples: we have to use client authentication, as in a client ID and a secret, or a key-based authentication for every flow with a security token service. That's a major improvement for security. Also, we can use sender-constrained tokens in the backend, which is basically a proof of possession mechanism that would prevent someone with a stolen access token from using it without knowing a secret that only our backend knows. And this is a BFF, or a backend for frontend, and this is the recommended best practice today for building sensitive SPAs dealing with APIs. I'm actually working with a couple of clients on implementing this pattern and overcoming certain challenges that you might see with that. That brings me to 3 key takeaways for this presentation and the wrap-up. First takeaway, use the authorization code flow with Pixie over the implicit flow. If you have a new project, it's a done deal. If you have an existing project with the implicit flow, I recommend looking into upgrading. If you're using an SDK, it's going to be really easy to do so because the details will be hidden. Use short access lifetimes, access token lifetimes, 5 minutes, 10 minutes, if you can get away with that, and rely on refresh tokens with refresh token rotation to obtain new ones. And if you're dealing with sensitive applications that deal with sensitive data, with high value transactions, I recommend to avoid tokens in the browser altogether and to focus or to build a BFF which handles tokens. That's essentially 3 key takeaways based on what we saw in this session right here. If you want to know more, you can either dig through dozens of specifications, it's a fun experience for sure, but I also built an online course that covers OAuth and OpenID Connect in a lot of detail, so I recommend you give that thing a look. There's a 25% discount until November 3rd if you want to take advantage of that. The URL is courses.pragmaticwebsecurity.com. And with that, I want to thank you for watching. I want to invite you to connect on social media. If you want to know more about security, I often tweet or post on LinkedIn about security topics and resources. So I hope to see you there. And if you have any feedback, don't hesitate to let me know.